I hope almost all of you are aware that there was a new standard published, especially for DC charger. It's actually not new, it's in a so-called edition 2, so that's the IEC 61851-23, specifically for DC chargers. That standard has been published in December last year, so it's just a couple of months. And I'm not sure if you have exposed to this standard. If yes, then I actually have a question to you. Do you believe that standard is going to improve the reliability, interoperability, and let's say customer experience charging electric vehicles for DC charging, of course? So maybe once we are through this presentation, I would be more than happy to hear your feedback, whether you actually think it would improve. Now, a part of that IEC 61851-23, the good thing is that also the new US standard SAE J1772, which has been published in February this year or January this year, is pretty much aligned with the IEC 61851-23 when it is about DC charging, so the characteristics, the performance requirements for DC charging, which actually is a good thing. And, well, why do we actually need to talk about that? So, well, it's always the same story. If you look at these statistics and press releases here on the left side or on the right side, left side from your side, that's more in United States. The majority of charging stations in the US appear not to work. In Europe, we have the German government, which is every month publishing a statistic where it says how many of the attempted charging sessions were successful and how many of the chargers actually were available. So if you look at the top, it basically means that about 8% of charging sessions in Germany are terminated within 2 minutes. So that means they are not successful. And the lower part of the statistic shows that about 5% of the charging stations are not available, so they are down. Again, that's a statistics which is being published by the German government. Now, we have those two new standards, both to describe requirements, performance, reliability, but also interoperability requirements for DC chargers. They are not new, so these are updated version. The -23 version, as said, is edition 2. So the first edition has been published in 2014, so it's just about 10 years ago. And of course, many things have happened in the meantime. I think development of chargers, DC chargers in particular, has sped up. More and more power has come, the voltage has increased. The old standard basically talks about DC charging up to 500 volt. Now we know that 500 volt nowadays is no longer enough. So a typical passenger vehicle can go up to 900 volt, and when we talk about megawatt charging, we go actually very close to the limit of the low voltage range, as we call it, which is 1500 volt. So it was about time to actually make an update of both standards. I want to focus on the IEC. What usually happens if we have an IEC standard, that IEC standard will be transferred also for Europe into a harmonized European standard. I have been told that this will not happen with this edition 2 for Europe, so that IEC 61851-23, it appears will not be a harmonized European standard, which I think, if it's correct, is a disaster, because that means for the next 3 years, for Europe, the so-called harmonized standard still will be the old version 2014. Maybe you also have heard something. The reason for that apparently is that those so-called HAS consultants, which the European Union now uses for looking whether an IEC standard could be an appropriate European harmonized standards, they concluded that this IEC-23 does not meet the requirements to be a harmonized European standard. So that actually indeed again would be, in my opinion, a disaster. Okay. What are the differences between the old version, so the version from 2014 versus the version from 2023, so the edition 2? The structure basically has been aligned to the -1, which is kind of like the basic standard for charging electric vehicles. So in particular, it has been aligned to the current 2017 version, which in this case would be the edition 3 of that IEC standard. Electrical safety requirements have been revised and also a bit aligned, and it is today possible, let me see if that works, to actually test the electronics of the inverter based on this standard, IEC 62477, and or also based on this IEC standard 62368, which maybe some of you know is the standard for telecommunication equipment, which is a new type of standard because it looks at the hazards which could be potentially inside that product. So it is a hazard-based safety approach. That's also a good thing because DC chargers in many instances have new technologies inside where there is nothing basically known inside the standard on how this should be evaluated, and if you do it based on a hazard-based approach, then even if nothing clearly is described inside the standard, you will be able to come to a conclusion. So, also one of the major changes is that test methods for checking conformity to the stated requirements of that edition 2 have been added. That is something what the old standard was completely lacking, so there were no test procedures described, nothing, there were just requirements but nothing on how to test them against. And that is now different, so the edition 2 has very clear testing requirements. Some of them we will discuss a little bit later. So generally, of course, also other charging standard systems are being described there. So like here the Annex A is the so-called System A, which would be CHAdeMO, and System B, which would be the GPT standard. Our focus of that international standard will be on the CCS part, so which is the so-called System C. All requirements, performance, quality, and reliability requirements basically have been updated. So not only for the CCS standard, which is being used in Europe and United States and other countries, but also for CHAdeMO and GPT. Oh, that was the wrong way. Yeah. There is also a slight difference inside the definition. This you basically can see here. So typically we were referring to a charging session when we were discussing about plugging in until we plug out. So the new standard now actually talks about a coupling session and no longer a charging session. It will take some time to get adjusted to that, but that is okay. What also has changed is kind of like the description of controlled current charging, controlled voltage charging. So that is now called controlled current mode and controlled voltage mode. So this is some essential functionality of the DC charger. And we also have now clear specification on what we call the site A. So site A is the grid-facing site, and the site B is the EV-facing side of chargers. It is important to understand that when we go through that standard, which also, amongst others, has almost 3 times as many pages as the edition 1. we have to clearly understand what requirement does apply to the side A, so the grid-facing side, and what requirement does apply to the side B. Again, also for the next couple of minutes, we will focus mainly on the side B. Also, something what has been introduced is rated boost current. So that is a current which a charger can sustain for a short period of time without that any kind of temperature limits are exceeded. So that is now also a part of that standard. When we look at functional requirements, they mainly have been remaining identical. However, there are 3 requirements which have been added. One of them is the maximum allowable current. Another one is voltage limitation at the side B, and a shutdown of the EV supply equipment. Shutdown means, for example, normal shutdown or also emergency shutdown. It will not be possible to give you all the differences, but I will pick out some essential differences, and I also will give you some examples why it is core to make sure that actually the industry should try to comply with those new requirements. So one of the first one is the output current regulation, which has been aligned, improved, and also, of course, taken into account that in the meantime, output currents can be in excess of even 600 amps. Also, again, that would be only for a limited time. So in case, for example, for this rated boost current. So we do have new limits for 3 ranges. That means when the current is below 5 amp, between 5 amp to 50 amps, and everything what is above 50 amps. And again, that's about the accuracy or to be aligned with the so-called EV target current. Certainly, you can ask yourself the question, does it matter? And yes, it does matter. That's what we have found during a charging session. And you can see multiple problems here. So, first of all, I think I have to do it here. First of all, the target current was a straight line at, here in this area, 277 amps. So the vehicle requested exactly always the same current. And when you then look on what actually has been measured, then you see here something, quite a huge range between the maximum current and the minimum current. Needless to say that this kind of fluctuation or ripple current or poor control of current also produces a lot of supraharmonics, as we just understood before. Not only does it produce supraharmonics, but of course it also produces emission. So it's not good for the grid, and it's surely not good for the charging, right? Here in this case, as we can see, I have to say the charging session was successful. So the electric vehicle was able to take that, for whatever reason, I don't know. But we were actually asked to do measurement because on this DC charger, from time to time, charging sessions have stopped for no reason. We were not able to actually duplicate that, but we had a we suspected that there is something not correct. What we did, we introduced some filtering for actually measuring the current, and we still did see that the current here is fluctuating quite a lot, even if you introduce a filter. So that means we already eliminated the high frequency part, so to say, but we still had a lot of fluctuation here in this area. And again, if you look at the target current, that basically is a straight line, so the electric vehicle always asked for the same current. We were able to obtain, because we were not able to duplicate that, but we were able to obtain PCAP files from another electric vehicle, where we basically only could work with the values which are actually being communicated during a charging session. So, I think I have to do it here again. And of course, we saw that something happens here. So when you look at the EVSE present voltage, that's the voltage which is being measured, and you also look at the current, you see that there are negative peaks. And what we found, that once such a peak here occurred, that the charging actually stopped because the electric vehicle was sending a message and saying, okay, something isn't right, and basically provided this full message, and the charging session has been terminated. I think in this case it was about after roughly 3 minutes here, as we can see here. So this kind of charger, which does not comply with output current regulation, at the same time also doesn't really comply with ripple current, they are in the market, and of course there might be just simply the reason that charging sessions prematurely terminate and the user doesn't really know that. So that's really something what we as an industry have to improve. Okay, so that would be the voltage current limit. So in principle, what we did see before, there are 2 issues. That's the current regulation, but also the voltage and current limits which are exceeded based on the new standard. Other issues which are being addressed inside the new standard is the temperature monitoring. So that is also very important. And what we have now, we have requirements that when the temperature is exceeding 90 degrees centigrade at the connector for more than 8 seconds, the EV supply equipment, so that means the charging station, basically should reduce the current or trigger an error shutdown, terminate the session, right? That is also something which was not the case before. And there has been an extensive test case defined to check for compliance against that requirement. So essentially the charger will be operated for a period of 1 hour to make sure that either it stays below that limit, or if it exceeds that limit, that it basically shuts down or reduces the current before those 8 seconds have been reached. That's over temperature protection. What is now also defined is that chargers have to be tested at 40 degrees centigrade with, let's say, the rated requirements, so at rated power and rated current. Also something which was not the case before. Okay, another essential improvement, that's the cable check feature. The cable check is here to ensure that the safety, before the charging process actually starts, that the safety is ensured. So what we do during the cable check is to make sure there is no isolation fault or whatsoever. Also, their test cases have now been defined to check that. There are also 2 approaches to the cable check voltage. So, for example, if the electric vehicle maximum voltage is below 500 volt, then the cable check voltage is either 500 volt or the EV maximum voltage plus 50 volt, whichever is higher. And if the electric vehicle voltage is more than 500 volt, then it's either 1.1 times the electric vehicle voltage or the maximum of the charging station voltage. So we actually have varying voltages for the cable check. And again, it's important to understand that this is a safety test or a safety check. And also there, of course, we do see a lot of problems. We see problems that, in fact, no cable check is being performed, or the cable check is being performed at wrong voltages. So this, I think, here was a good example at 800 volt. So the charge did go up at 800 volt. And this one here, for example, let me have a quick check. What's the EV maximum voltage? Is 825, but we see that the cable check only went to 500 volt, which basically would not comply with the new standard. Other problems which we observed in the market and which now also has been clearly addressed is the fact that chargers sometimes need to shut down for emergency reasons. And one of the more important shutdown procedure is if the electric vehicle initiates emergency shutdown. So if the EV thinks, okay, something doesn't go well anymore and I immediately need to stop the charging. What we have now is we have a so-called reaction time of 10 milliseconds or less. And that's a bit different from before. And what it basically means, within that reaction time or trigger time plus the reaction time, there are about 30 milliseconds to make sure the current is below 5 amps and is below 60 volt to create safe conditions. So also here, if you look, let's say, let me skip that, let's go to this one directly. If you look at what we see on the market, we see times of 46 milliseconds until it actually is triggered, and we have times of approximately 40 milliseconds below, before the current is below 60 amps, and another roughly 100 or so milliseconds before the voltage will drop below 60 volts. So also that, in fact, could be a safety hazard. Also here, I think that is even more extreme. So the trigger time and the reaction time of reducing to current below 5 amps was like 428 milliseconds, and for the voltage it was about 2 seconds. Too dangerous, very clearly too dangerous. Should not be the case. We also spoke about cable check voltage. So also here we did see many different things. So in this case here, we did have a cable check voltage, but when you look at the time for the cable check voltage to actually decrease to 0 so that the pre-charge can start, you will see that this time is quite long. And what happened is that in that phase, the EV will some sort of trigger a pre-charge timeout. Typically, the pre-charge is very short. And if you are not able to achieve that pre-charge because of some problem with the cable check, the EV basically will shut down and say something is not right. We also did see that on the market, so that we actually have no cable check voltage applied whatsoever. And that, of course, again, should be a no-go, right? Okay, to summarize that, there are many new requirements, and for all of those new requirements, the good thing in this new standard is there is now a way to test them, and everybody would do the testing in exactly the same way because it's all described inside the standard. And again, those tests will make sure that we have a certain guaranteed functionality, a certain minimum level of performance and quality, and of course, still again, what is important, that the chargers are actually safe. And I honestly believe by complying with this new standard and making sure it is tested according to that new standard, it will really help improve the overall situation with regards to unreliable charging. That's my personal opinion. And now, actually, the question to you would be, do you believe that as well?